My friends, we're going to go over limiting reactants and excess reactants and yields, and we're going to go through every scenario, pretty much every scenario that you'll see on a midterm or final exam or a quiz or anything like that. And I'm going to explain everything fully in detail. So after this video, you're going to feel like you're good. I'm awesome. I know this stuff. I know limiting reactants, and I'm ready for it on the exam. So we'll jump into it with some real exam problems. This is the first one. It's given to real students. And it goes acrylonitrile C3H3N can be made as follows. And we have this balanced chemical equation. And we want to know, this is part A, but there's 3 parts just to show you here. What mass of acrylonitrile can be made from 21 grams of C3H6, that's this reactant, and 22.0 grams of NO, that's this reactant. And then we want to know how much of the excess reagent remains. And then if the percent yields 83%, what's the actual yield? So I'm going to put these ones away, and we'll focus on part A. Now, the important thing to know when you look at a chemistry question is what type of a question is this? And this is a limiting reactant question because we have a balanced chemical equation and we have a certain amount, in this case mass, of each reactant. So if this is the case, then we know that very, very likely one of them will be used completely. One of these will get used up completely, and there'll be a little bit of leftover of the other one, the one that's in excess. And we want to know how much of our product we can make. So this is a limiting reactant problem. And to do that, we'll look at each reactant separately. So we'll start off with the C3H6. And based on this, the given amount is 21.0 grams of C3H6. We want to do stoichiometry to determine how much of our product this could make, assuming all 21.0 grams reacted fully. So we're going to ignore the other reactant for now. And to do the stoichiometry, if you're a little confused at doing stoichiometry from here to here, I made a video on stoichiometry. It's an easy 3-step process. It's 14 minutes of your life. Strongly recommend checking it out if you haven't, because you can get stoichiometry correct every single time because it works every single time. So I'm going to explain the stoichiometry, but I will go through it relatively quickly. So this is stoichiometry because we have a balanced chemical equation. We have a given amount, or in this case mass, of one chemical in the equation, and we want to know something about another chemical in the equation. So we will do our 3 steps. So we'll go from grams to moles. We got to do a mole bridge eventually. And we want grams to cancel out. So grams of C3H6. And we want moles. That's always step 1, moles of C3H6. And for every 1 mole, if you look on the periodic table, each carbon has a mass of 12.011 grams per mole. Each hydrogen is 1.00 grams per mole times 6. So the molar mass of this compound is 42.081 grams. Our grams of the compound cancel out, and now we can do the mole bridge to get to moles of our desired product. And we have moles, we'll do the units first, moles of C3H3N, and we want the moles of C3H6 to cancel out. And according to the balanced chemical equation, it's a 4-to-4 ratio. So 4 moles of product for every 4 moles of this that react. So that's fun. And when you do this, I strongly recommend writing the compound name. This is moles of what? So the moles of C3H6 has to cancel out with moles of C3H6. It won't cancel out with moles of this. It has to be the same unit and compound for it to cancel. Okay, so now that we have moles of C3H6, we can go to mass. And we want moles of C3H6, and, C3H3N, C3H3N to cancel out. And we want to know how many grams of C3H3N there are. For every 1 mole, if we look at the periodic table, add up the molar masses of all these elements, we should get 53.064 grams. Okay, and it's always fun to cancel our units out to make sure we're in the proper units. Okay, so we'll plug that into our calculator. Just move this down a little bit here. And so 21 divided by 42.081 times 4 divided by 4, which is just 1, but I'll put it in there anyways. 53.064, 26.48. 26.48 grams of C3H3N. So this number tells us this is how many grams. Oh, this is kind of messy here. This is how many grams of C3H3N we could produce, assuming all of these 21 grams reacted completely. Now let's look at the NO to see how many grams of the acrylonitrile we can make, assuming all of this NO reacted completely. So we'll do the same thing, stoichiometry. So we'll start off with 22.0 grams of NO. And then step 1, we go to moles. Moles of NO. We want grams of NO to cancel out. And for every 1 mole of NO, we look at the periodic table. It's 30.0061 if we add up the molar masses of nitrogen and oxygen. So grams of NO cancel. Now we have moles of NO. Now we could do the mole bridge based on the chemical balanced equation, actually. And we want moles of NO to cancel. I always do the units first to make sure our units work out. And we want moles of C3H3N. C3H3N. And the chemical equation says for every 6 moles of NO that reacts, we produce 4 moles of C3H3N. So this is a 4 to 6 ratio, and our moles of NO cancel out. That's fun. Sweet beans. And now that we have moles of C3HN, we want to go to grams. So we want grams of C3H3N, and we want to cancel out our moles of C3H3N. And we'll use the molar mass. I'll just clean this up a little bit here. For every 1 mole of C3HN, C3H3N, it weighs this number here, 53.064 grams. Okay, so I'll plug that into the calculator. 22 divided by 30.0061 times 4 divided by 6 times 53.064. I really like these calculators where you can see what you type. It's, yeah, that's awesome. Okay, 25.94. 25.94 grams of C3H, that's a 3N, and our units cancel here. Okay, so if we look at this, if our C3H6 reacted fully, all of these 21 grams reacted, we have enough C3H6 to make 26.48 grams of C3H3N. But we only have, but for NO, if we only have enough NO to make 25.94 grams. So this NO, the nitrous oxide, this one is limiting how much product can form, how much product we can make. And that's the definition of the limiting of a limiting reactant. So this is our limiting reactant, or LR, because it produces the least amount of product. Produces the least amount of product on paper, in theory, the theoretical. So this is limiting how much acrylonitrile we can produce. We have enough C3H6 to make 26.48 grams, but we can't make 26.48 grams because we only have enough NO to make 25.94 grams of acrylonitrile. So this is our yield. This is how much now this is how much can be made. We should actually write in how much can be theoretically make, theoretically made, because this is on paper. Sometimes what happens in the lab stays in the lab, so to speak. Not every reaction goes well, or not every reaction goes to completion as well. So this would be how much we can theoretically make. This is our theoretical yield. Theoretical yield. Great. Okay, that means if this is our limiting reactant, NO is our limiting reactant, then the other one is our excess reactant. It's the one that's in excess. Alrighty, let's move on to part B. And this type of question comes up all the time on exams. How much of the excess reagent remains? And this is very important when you're doing chemistry because we don't want too much reagent to remain, if possible, and we need to know how to isolate it and things like that. So let's find out how much. Now the excess reagent is excess is C3H6. That's our excess reactant. And we want to know how much of this C3H6 was used up. Well, our limiting reactant was NO. So that means this NO is going to react with some of this C3H6. So these 22.0 grams, this is going to react fully, in theory. This is going to react fully, but it's not going to react with all of these 21 grams because this one is in excess. So there's going to be a few grams remaining. We want to know how many grams are going to remain after this reacts, after these two react. So we're going to need to know how much grams of this reacts with the NO. So we're going to start with the NO, and this is again stoichiometry because we have a given amount of one of the compounds in a balanced equation, and we want to know something about another compound. We want to go from grams of this to find out how many grams of C3H6 it reacts with. So we'll start with the NO, and there's 22.0 grams. Oh, one thing I want to say, very, very important, check this out. Okay, so C3H6, there's only 21 grams to start with, right? There's 21 grams, but we have 22 grams of NO. So we have more grams of NO. So we have more NO than C3H6. However, even though we have more grams of NO, a greater mass of this reactant, this one is still the limiting reactant. So the limiting reactant, it's not the one that we have the less of. The limiting reactant is the one that produces the least amount of product. And the only way you can do this, unless you can do it in your head for some kind of magic reason, if you're a math whiz or something, the only way to do this is to go through the stoichiometry and figure out which one produces the least amount of product. Okay, or do some kind of stoichiometry. There's another method I'll show you in the next question, but this is basically the way to do it. Okay, so we'll start off with 22.0 grams of NO to find out how many grams of C3H6 reacts with these 22 grams of NO. So these are grams of NO, and we got to go to moles of NO. So we'll write the units first, moles of NO, and we want grams of NO to cancel out. For every 1 mole of NO, we look at the periodic table. It weighs 30.0061 grams. So our grams of NO cancel out. And we want to get to moles of C3H6. So we'll put moles of NO downstairs to cancel out. And we want moles of C3H6. And based on our periodic or our balanced equation, 4 moles of C3H6 react with every 6 moles of NO. So it's a 4 to 6 molar ratio, and our moles of NO cancel out. Now that we're in moles of C3H6, we can find out how many grams reacted with these 22.0 grams of NO. So we want to cancel out moles of C3H6. So moles of C3H6, and we want grams of C3H6. So the molar mass of 3 C's and 6 H's is 42.081 grams for every 1 mole. And our moles of C3H6 cancel out, so our only unit is grams of C3H6, which is what we want. Alrighty, we'll plug that into our calculator. And 22 divided by 30.0061 times 4 divided by 6 times 42.081 gives us 20.57. There's 3 sig figs here. Oh, did I do the right? I'll go back in a minute. 20.57 grams. 20.57 grams. We actually only have 3 sig figs here, right? So we're only significant to 3 sig figs here. And make sure you write the units and what the compound is. That's very important, so you don't get confused. Okay, so if what this says is that if all of these 22.0 grams of NO react, they need 20.57, 20.6 grams of C3H6. So this is how much will react when all of our NO reacts fully. Well, how much of the excess reactant remains? So we can say mass remaining. And most of us can kind of come up with this equation in the head. How much do you have left over? Well, you have the initial mass, how much you started with, initial mass, and you got to subtract that initial mass from how much mass reacted, how much was used up. Mass reacted. Okay, well, we started off with 20, was it 21.0? Gotta double check. 21.0. Yep. 21.0 grams. And we reacted of that 21.0 grams, 20. Oh, look at it. Okay, no, it's okay. The sig figs work out. 20 point, it's very close. Almost not much remaining, but there's a little bit left remaining. 20.57 grams. Okay, and I recommend using one or two more digits than you actually need if you're going to use this number in further calculations. And so you only round once at the very end. 20.57. Okay, so 0.43 grams. 3 grams of C3H6. Now, this is significant to 1 decimal place, same as this one. Therefore, our answer is only significant to 1 decimal place. So your full answer would be 0.4 grams of C3H6, just 1 decimal place here. Wanted to go back. So here, what mass can be made? We have 3 sig figs. So our answer, and these are exact units, the mole bridge, molar ratio. So our answer should only have 3 sig figs as well, not 4 here. So this should be 25.9 grams of C3H3N for full marks. You'll lose a partial mark if you don't do sig figs, probably, unless your prof doesn't care, but most do. So there we go, 3 sig figs. Okay, life is good. All right, next, like super common part that you'll see on your midterm and final is if the percent yield is 83%, what's the actual yield? And you just kind of got to remember this equation. Percent yield, it's intuitive for some of us, equals how much you made, the actual yield over the theoretical yield. Theoretical yield. And times 100% because we want it to be in a percent. And I remember this as A over T, so it's in alphabetical order. Percent equals A over T, just like that. Okay, percent yield's 83%. And we want to know what the actual yield is. I'm just going to abbreviate as AY, if that's okay. And the theoretical yield is how much we could produce based on the limiting reactant, assuming the reaction went to completion and was perfect and all that stuff. So the theoretical yield is a calculation yield. Maybe I should write that down. This is a based on calculations. So based on calculations and the limiting reactant. And the actual yield is what you get in the laboratory. So this is what you make, what you actually make. What you actually make. So what's staring at you on the balance when you put it back on the scale, the white powder or whatever you make when it's looking at you after spilling it on your partner and stuff, that's your actual yield. Theoretical is just how much we kind of theoretically make based on the limiting reactant. So we go back up here and we can theoretically make 25.9. I'm going to keep this extra digit because we don't want to round until the very end unless we're reporting it. So 25.9, whoops. It's not really going to matter for sig figs because we only have 2 here, but it's good practice. All right, so plug that in. I'll do the algebra actually just so you see it. So if we solve for the actual yield, it's going to be equal to, oh, this is times 100%. Right, the equation has 100% here, so I got to put the 100% here. So the actual yield equals 83% times 25.94 grams divided by 100%. That way our percent cancels out and we're left in grams, left with grams. 83 times 25.94 divided by 100. And our actual yield is 21.5 grams. It's less than the theoretical yield. It should always be yet less, unless there's some error, instrument error, or it's wet, it's not fully dry or whatnot. So 21.5 grams. Here we only have 2 sig figs. 21.5 grams. Unfortunately, the percent yield is only in 2 sig figs, which is usually how it is. Usually percent yields are rounded to whole numbers. So we would report this as 22 grams of C3H3N acrylonitrile. Okay, this next one here is also very common. In this case, we have a balanced chemical equation as usual, but in this case, we don't have masses of each reagent. We have solutions and we have volumes and molarities. And we're going to do limiting reactant problems with solutions here. So this is a solution-based problem for limiting reactant and yields and whatnot. And we'll do the same things. What is the limiting reactant? What is the concentration of the excess reactant? What is the theoretical yield? And then if the actual yield is this, 0.1530 grams, what is the percent yield? So these questions are common as the color blue in this topic, so to speak. So we'll jump into it. And I'll show you 2 ways to find out what the limiting reactant is. So I'm going to give a little bit of space here. And this is one of the more common ways that I see students do, and there's nothing wrong with this, totally fine. What I see is we start with one reactant, say the iron 3 chloride, and we figure out how much of the KOH we need to react with all of this FeCl3. So we'll start off with our FeCl3, and there's 35 mils. I'm just going to convert that to liters. Let me know if you're not sure how I did that, and I can put in the comments or make a video on that. But we have 0.0350 liters of FeCl3, and we want moles because we're doing stoichiometry here because we have a certain amount of one compound, and we want to know something about another compound in a balanced chemical equation. So that's stoichiometry, 3 steps. Okay, so first we got to go to moles, and we know that there are, now this capital M, remember it's a hidden unit. It means MOL over liters. It's moles per liter. So every time you see this, you can break it up into this. And since it has 2 units, it's great to convert units. So there are 0.100 moles of FeCl3 for every 1 liter of FeCl3. Now that we're in moles of FeCl3, we can use the mole bridge to get to moles of KOH. So we'll put in this here. Now we want moles of KOH. We want to cancel out moles of FeCl3 based on our balanced equation. For every 3 moles of KOH that react, we need 1 mole of FeCl3. Now for our units, wait a second here. Oh yeah, this cancels with this one right here. Our units are in moles of KOH. And okay, so let's do that. So we have moles of KOH, and we can find out how many moles of KOH we have. 0.035 times 0.1 times 3, 0.0105, 0.0105, and we had 3 sig figs as before. Okay, so that's how many moles of KOH we need. How many moles of KOH do we actually have? Well, there are 25 mils, so 0.0250 liters of KOH, and we'll convert to moles using the molarity here. There's 0.200 moles of KOH for every 1 liter of KOH. So liters of KOH cancel, And if we plug this in, don't really need a calculator, but I'll put it anyways. 0.2, 0.005. So 0.005. Now there's 3 sig figs here and here, so I better make this 3 sig figs. Moles of KOH. All right, so look at this. So the iron 3 chloride needs 0.01 moles of KOH, but we don't have 0.0105 moles of KOH. We don't have this much. We only have 0.005. So we don't have enough KOH to react with all of the iron 3 chloride. Therefore, this is our limiting reactant. This is our LR, and then this one has to be the excess reactant. So that's just another way to find out the limiting reactant. The limiting reactant is the one that produces the least amount of product. And to do that, you could also figure out which one doesn't get used up fully by looking at the reactants. Okay, so now what is the concentration of the excess reactant? So that must be after it reacts, of course. Sometimes they don't say these things, but that's what they are. Whoops, there we are. Okay, all right, so the excess reactant is this one. So we want to know how much of this reacted. Well, we need to know how many moles of FeCl3 reacted with the KOH. So since we know this KOH reacted fully, or we assume we do, theoretically, we'll start off with that. So we have 0.00500 moles of KOH, and we want to know how many moles of FeCl3 we need. So we use the balanced equation to go from moles of one compound to moles of the other. We want moles of KOH to cancel out. We want moles of FeCl3. And on our balanced equation, for every 1 mole of FeCl3 that reacts, we need 3 moles of KOH. So it's a 1 to 3 ratio. Okay, so we can divide this by 3. Divide by 3. 0.001667. 0.00166. Let's put one more. Oh, no, we don't need too many. I'll just do one more than we need. Sig figs. Moles of FeCl3. So this is how many moles reacted in theory if it goes to completion. So how many moles remaining? See, if we want to know the concentration of the excess reactant, we need to know how many moles of there are in our solution. So the moles remaining equals our initial moles, initial moles minus the moles reacted, or reacted moles, I guess, the number of moles that reacted. Okay, so how many moles did we start off with? No idea, but we can figure it out. We have this volume and a concentration, so it would be this first step right here will give us moles of the iron 3 chloride. So 0.0350 liters. And there are, was it 0.1? Yeah, 0.1. 0.100 moles for every 1 liter. I know this is all iron 3 chloride, so I'm not putting the compound here because I'm not changing between compounds. How many moles reacted? This amount reacted. 1667 moles. And when we put this in our calculator, we should get a positive number. You can't have negative moles, right? So 0.035 times 0.1 minus 0.001667. Okay, so that's good. So there's some moles remaining. 0.01833 equals 0.001833 moles remaining. So the concentration is simply, so concentration is moles over liters, moles over volume. We know that there's this many moles, 0.001833 moles. And what's the final volume? We're mixing 35 mils with this mils. Now these are both aqueous solutions, so we can generally just add these two together. If these are different, have different solvents or vastly different concentrations, if they're not that dilute, then you can't just simply add these numbers. But for relatively dilute aqueous solutions, you can just add this up. So 35 plus 25, 35 plus 25. So this is milliliters. And then we got to make it into liters. So for every 1 liter, there's 1,000 milliliters. So basically divide that by 1,000. Okay, alrighty. So 0.001833 divided by, that's just 60, right? 60 divided by 1,000. Okay. 0.03, so 0.0305, 0.03055 moles over liters, which is molarity, capital M, of FeCl3 remaining. Do you see that? I hope that makes sense. Let me know if this isn't making sense to you. Now, we have 1, 2, 3, 4, 1, 2, 3, 4. Oh, actually, look at this. No, there's 3 sig figs. We're good. This is 3 sig figs here. That means 1, 2, 3, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Okay, so this is only significant to here. So we should only report to these 3 digits here. Significant to here. This 3 sig figs. These are, this should be 3 sig figs, 35.0 minus 25.0. So this has 3 sig figs, 3 sig figs. So this one should have 3 sig figs. So it'll be 0.0306 moles per liter. Cool beans. Okay, great. Radio. So I know these questions are kind of long, but there's not really much way around it. What is the theoretical yield of, we're not making this. Why did I do Cl3? FeCl3 should be OH3. Of OH3. There we go. Okay, life is good. What's the theoretical yield? Okay, so the theoretical yield is based on the limiting reactant. And when we determine the limiting reactant this way, we're using this method, we don't know what the theoretical yield. But if we determine which one is the limiting reactant the other way, like I first did in part A, the one that produces the least amount of product, then we get the theoretical yield right away. That's why I prefer this method in determining the limiting reactant, because you also get the theoretical yield at the same time. It's kind of like a 2-in-1, but it doesn't really matter, and it doesn't really save too much time, but I do like to do that 2-in-1 the best. So the theoretical yield is based on the limiting reactant, which was KOH. No, yes. And how much KOH do we have? We have 0.00500 moles of KOH. 0.00500 moles of KOH. And we want to find out grams. Okay, well, we got to use the mole bridge. Every time we go from one compound to another in a balanced equation, we need to do the mole bridge. And we want to cancel out moles of KOH. We want moles of Fe. I feel like I did FeCl3 somewhere else too. FeCl3 right here. OH3. And again, everywhere. I think I was stuck on the same question before. Okay, all of these should be OHs. Look, oh no, this is FeCl3. Oh, and this is FeOH3. Right, okay. This is Cl3. I was right there. This is Cl3. Okay. Getting my Cls and my OHs mixed up. Okay, there's a 3 moles of KOH to 1 mole of FeOH, so Fe iron 3 hydroxide ratio. So it's a 1 to 3 ratio. Moles of KOH cancel out. Now we don't care about moles. We care about grams, right? So we got to get to grams. And we got to cancel out moles of FeOH3, OH3, and we want grams of FeOH3. And for every 1 mole, based on the periodic table, if we add up the molar masses of all the elements, 1 mole weighs 106.87 grams. Okay, we'll plug that in. 0.005 divided by 3 times 106.87. 0.1781. 0.1781 grams of FeOH3. And we have 3 sig figs, so 0.178 grams. This is how much we can theoretically make. We might not make this much, but on paper, if this limiting reactant was consumed completely and reacted fully, we would produce 0.178 grams of iron 3 hydroxide. Okay, last part of this question, that this is always comes up in some form. If the actual yield is this many grams, what is the percent yield? So we have our wonderful equation, one equation for all 3 yields, percent yield. Oh, what am I doing? Percent yield equals actual yield over theoretical yield times 100%. That looks better. We want the percent yield. The actual yield is this number here. This, you can't calculate this number. This number is obtained from experiment only. You might calculate it if we get the other 2 numbers, the other 2 yields, we can calculate it, but you can't get this based on just theoretical math only. Okay, what's our theoretical yield? It's 0.1781 grams, and multiply that by 100%. Now we're going to do this, and there's something very important afterwards. And some profs care, some profs don't care, but I'll mention this. So 0.1781 times 100%. So 85.9%. 85.9. I'll make that a better 8. 85.9%. Now, it's good practice, even though that this is 3 sig figs, this is 4. Our answer should have 3 sig figs, right? But it's good practice to round your percent yields to the nearest whole number, even though we have 3 digits of precision here. And the reason is that the error that we did in the lab, if we were to repeat this experiment, we probably wouldn't be precise to 1 decimal place. I should say, yeah, precise. We probably wouldn't be reproducible to 1 decimal place. So it's, if we were to redo it, we probably wouldn't get like this same number, or a 0.8 or 86.0 or 86.7. Like, it'd be a lot off usually if you repeat the experiment. Usually several percent or even more. It could be off unless you've done this experiment like hundreds of times. You're in grad school, you're doing research. So generally the error that goes on in the lab and repeating the experiment is a lot greater than the precision of your measurements alone. So we often report yields, percent yields, to nearest whole numbers. Okay. Some profs care, some don't, but anyways, there you go. So my friends, your prof might try to mess you up with weird units for limiting reactant problems. So these are 2 examples here, one with a liquid and one with a gas, so that after this you will be good. You'll have covered the bases, and even if your prof tries to throw you for a loop, you've got it covered, and you could succeed even if your other classmates fail or whatnot, or send them this video anyways. Okay, so this is the example here, and this is a real exam problem that came up. If 5.40 milliliters of bromine, now we have a volume and a density, that's it, reacted with 150.0 mils of C2H2. So this would be ethine. It's a gas right here. 25 degrees Celsius under a pressure of 1.1 bar, that's the pressure, to produce a percent yield of 85%. What was the actual yield? Now, we know this is a limiting reactant problem because we have a balanced equation, And always check, make sure your prof has it balanced. Sometimes they try and throw you for a loop and not balance their equations, and you have to do it without telling you, but this is balanced. And we have information, we have initial conditions for each reactant. So if we do that, one of these are going to be in excess, and one of them is going to limit how much of this we can make. So we're going to look at each reactant separately. We'll start off with the bromine, and we're going to look at if all of these 5.40 milliliters reacted fully, how much of this product, this tetrabromoethane is what it is, but can we make? So we're going to do stoichiometry to go from amount of bromine, volume of bromine, to grams of this product here. This is stoichiometry, 3 steps. You can check out my 3-step process if you're confused. But I'm going to go through this relatively quick. So we want to get to grams of this product here. So we're going to start off with 5.40 times 10 to the negative 3 liters. That's just converting this to liters here. Now we want to get to moles first because we need to use the mole bridge to find out how many moles of this product there are. So we can't go from liters to moles right away. We have to cancel out with this density. Oh, this density is in mils. So actually, let's make this milliliters here so that we can cancel out the milliliters. And this is of bromine, Br2, Br2, and we want to cancel out milliliters of Br2. We want grams of Br2, and bromine weighs 3.12 grams for every 1 milliliter. So now that we're in grams of our one reactant, we can go straight to moles using the molar mass like we've always done. We want grams of Br2 to cancel out, and we want moles of Br2. For every 1 mole of Br2, we can look on the periodic table. Molar mass of bromine times 2 is 159.809 grams. So our grams of Br2 cancel out. Now that we have moles of bromine, we can use the mole bridge to find out the moles of this product here. And so we'll do that. So we will, for every, maybe I'll make it a little bit smaller, just to save space. So I have enough space. We want moles of Br2 to cancel out. And we want moles of this product. Moles of, I'm just going to call this P for product, if that's okay, just to save space. And for every 2 moles of Br2 of bromine that react, we make 1 mole of product. So there's 1 mole of product for every 2 moles of Br2. Moles of Br2 will cancel out. So we will get 1 point, that'll give us moles of product, but we want grams of product, right? So let's go to grams here. And we want moles of product to cancel, and we want grams of product. Now the molar mass of this, you can look in the periodic table, 2 times the molar mass of carbon plus 2 times the molar mass of hydrogen plus 4 times the molar mass of bromine works out to be 300. So for every 1 mole of the product, we get, it weighs 345.7 grams. Okay, now we'll plug that into our calculator. So 5.0 times 3.10 grams divided by 159.809 grams divided by 2 times 345.7 and 18. Does that make sense? 18.22 grams. 18.22 grams of our product, which is C2H2Br4. And 3 sig figs, so we have 3 sig figs here. So this is how much we would produce if the bromine reacted completely. But we need to look at the other reactant, the C2H2, to see how much product we would produce if it reacted completely. So we're going to look at the other one, C2H2, and we need to know how many moles of this there are. Well, we don't have a volume or a mass. We have a gas, and we have a volume, a temperature, and a bar. So we have these gas conditions. So in order to find out the number of moles based on gas conditions for a gas, we need to use the ideal gas equation, or the perfect gas law here. PV equals nRT. It doesn't say so, but we're going to assume it's an ideal gas or a perfect gas. N is the number of moles. So N equals PV over RT. Now we just have to make sure that our units work. P is our pressure. So pressure is 1.1 bar. 1.1 bar. And our volume is 150 mils. I'm just going to put this into liters. So move the decimal over 3. 0.1500 in order to divide it by 1,000. Now, R is our gas constant. I'll do the R last because our units have to be in moles. So the temperature is 25 degrees Celsius. Now, we got to put that in Kelvin. So 25 degrees Celsius in Kelvin, we got to add 273.15 to get Kelvin. So that's 298.15 Kelvin. So the R we use has to cancel out bars, liters, Kelvin, and moles here. So we will use the one that is 8.314 liter bar per mole Kelvin. And it's always good to cancel the units. Bars cancel, these liters cancel, Kelvin cancel. So we have 1 over moles down here. So we could kiss and flip, and then we get moles for the units here. Same thing up here. I don't think I canceled my units, but moles of P cancel out moles of product, and we're left with grams of product. Okay, so let's plug this into our calculator. 1.1 times 0.150000 divided by 8.3145 times 298.15 is really small number. Okay, well, it is a gas. 6.656. 6.656. 6. Oh, I'll make it blue. 6.656 times 10 to the negative. Was it 5 moles? I better double check this. Okay, 5 moles, and this is of our product, C2H2. Okay, now that we know how many moles of our, not product, sorry, reactant of our reactant there are, we could find out how many moles of our product there are. And it's a 1-to-1 molar ratio. And I'll just write it out just so everything is complete. And your prof likes to see that as well, likes to see all the steps. Even if it takes 30 seconds or so, it's worth it. And it could save you in case you did a silly error. I sometimes do them. So we have moles of C2H2 that cancel out with here, and we want moles of our product. I'll just call it P, and it's a 1-to-1 molar ratio. And in this way, our units cancel, so we feel pretty good about ourselves. Oh, now that we have moles of our product, we don't want moles, we want mass, right? So we want to cancel out moles. Moles of product, we want grams of our product. For every 1 mole, the product weighs, what is it? 345.7 grams. 345.7 grams. Okay, we plug that into our calculator. So, oh, I just deleted the number. Oh well. 656. I could have put this in scientific notation. 1, 2, 3, 4, 5. Okay, I think that's good. 656 times 1 times divided by 1 times 345.7. 0.02301. 0.02301 grams of C2H2Br4. Okay, so we have this many grams, assuming that the gas reacted fully. But if the other one, bromine, reacted fully, we could make 18 grams. Holy. So we have enough bromine to make about a little more than 18 grams of product. 18 grams. We have enough bromine to make almost 18 grams of product. But we only have enough of the gas of the C2H2 to make like a fraction of a gram. This is like 23 milligrams of product. So we can't make this much product because we don't have enough of the gas, the C2H2. So this is limiting how much we can make. So our theoretical yield, I'm sorry if it's messy, equals 0.0230 sig figs, 1 grams. How many sig figs do we have? Oh, we have 2 sig figs here only. So this one doesn't matter. Yeah, we only have 2 sig figs. So 0.023 grams of C2H2Br4. Okay, so that's our theoretical yield. We want to know what the actual yield is based on the percent yield. So from that, we use our yield equation. Percent yield equals the actual yield, AY actual yield divided by the theoretical yield. I remember this is alphabetical order, A over T times 100%. Well, we want to know what the actual yield is. So the actual yield is going to equal the percent yield times the theoretical yield, all divided by 100%. And so what's percent yield? I think it was 85%. Is that right? Let's see here. 85%, that's right. 85%. Theoretical yield is right here. Oh, we'll keep this extra digit. Oh, it's a 0, but we'll keep one more digit and then we'll round at the end after. 230 grams divided by 100%. Okay, time to partay. We're almost done. Times 0.023 divided by 100. 0.01955. So 0.01955 grams. Because our percent yield is in 2 sig figs, and usually the percent yield is rounded to the nearest whole number. We're stuck to round here. We'll round the 5 up because this is an odd number. So 0.020 grams is our actual yield of C2H2Br4. Right on. Awesome possum. Well, hope you enjoyed it. Hope you got some benefit from it. I really enjoyed it. And after this example and the other examples that I've created for or the videos on limiting and excess reactants and yields and the 3-step stoichiometry method, you should be so good at this stuff. Practice, practice, practice. And I hope you do well in your exams. Thanks so much for watching. I'll see you in the next one. Cheers.